Okay. Hello, everyone. And my name is Haolin Li, and I'm now a postdoc at ITP Beijing. And my talk is based on these two papers, and I will focus on how to treat the repetitive field problem in a systematic way. Okay, let us start by defining the repeated field in operators. So the repeated fields are those fields with the same quantum numbers. And in this sense, two lepton doublets with different flavor indices are repeated fields, while the L and L dagger are not. So let's take a look at the simplest SMEFT operator that contain the repeated field, the dimension-5 Webpage operators. And probably people are all familiar with the fact that these operators is symmetric under the permutation of the two flavor indices. But the proof might not be as simple as you thought. Here I explicitly write down all indices of each field in these operators, and several steps are needed to convert the original operators into the one with the permuted indices. Okay, the previous slides shows that even for the simplest operators, it is not trivial to find the symmetry among the flavor indices. Then what about the more complex one, the 3Q1L operators? It turns out that originally in the published version of the VASA basis, it contained two terms related to this type of operators. And not until 2014, it was realized that these two operators can be, can you see my mouse? I assume you can see my mouse. Okay, yes. These two operators can be expressed by a single one with flavor indices permuted. And these single operators has the flavor relation included in these equations. So this is the traditional way to treat the symmetries among the flavor indices. You write a bunch of operators of a certain type of operator, and then you include those symmetries among the flavor indices into a set of equations like this. So there are disadvantages of this approach. First, it is negative to find this relation by hands. And with the increasing operator dimensions, the problem, these difficulties are enhanced. So since more and more repeated fields will appear. And second, the second problem is that even though in the reference 3, they provide a way to parameterize the independent Wilson coefficient of these operators. Well, in general, how to parameterize the Wilson coefficient, the information of how to parameterize the independent Wilson coefficient is not so easy to extract from a set of flavor relation equations. So how to solve these problems? Let us go back to the simplest example, LHH, and think about what do we really mean when we say something is totally symmetric or antisymmetric. It actually means the object we are considering is an one-dimensional irreducible representation of the corresponding symmetric group. And in terms of one-block operators, it is then a symmetric representation under the S2 group, while the Schur-Weyl duality in the group theory tells you that if you view this object as a tensor under the SU group, and the F1 and F2 becomes a variable that can choose from 1 to n Fn, then the independent component spanned by then this object is also represent the irreducible representation in this group, and the independent component of this space is given by the Sand model, semi-standard Young tableau of this corresponding Young diagram. So therefore, the form of observation is by that to solve the field problem, or to find the independent component of any types of operators with repeated fields, one should try to organize operators into the irreducible representation of the symmetric group. And for our notation, the 3Q and 1L contain 3 types of operators, and they serve as irreducible representation under the S3 group. From Professor Yu's talk, you might have already learned that for an arbitrary operators of a given type, and one can factorize the operator into the three parts: the gauge part, the Lorentz part, and the Wilson coefficient parts. And using the amplitude operator correspondence, one can find that the independent amplitude basis, which help us to construct the independent operator basis. And the independent gauge and Lorentz factors is given by the corresponding Young tableau, which is what we call the gauge and Lorentz Y basis. And once the Y basis is obtained, Lorentz and gauge Y basis is obtained, then one can just contract the group indices in this gauge between the gauge and Lorentz factor Y basis, and to obtain the so-called what we call the flavor blind operator Y basis. And this object with flavor indices expressed as different symbols so take a look at the example here. The PRST are the flavor indices, and this type of operators has two elements in the gauge Y basis and one element in the Lorentz Y basis. And this yields two flavor blind Y basis operators. And at this stage, the flavor indices are just different labels, and there's no meaning to discuss their values. Well, on the other hand, when considering this formal object as the tensor of the SUNF group, then these operators span the representation space of this group. And if there's no repeated fields in the operator, the space spanned by this operator are just disjoint, which pictorially shown here on the bottom left, where each circle represents the space spanned by the operators. And the dots in there, represent the independent component after specifying the flavor indices, which is what we call flavor specified operators. So things becomes complicated when there are repeated fields present in the operators. And in this case, the Y basis, flavor blind Y basis operators forming a complete reducible representation under the symmetric group. And as denoted as the triangle dots here, they are considered each Y basis operator are considered as then basis in the S3 symmetric group reducible representation space. And any permutation of the flavor indices, which is what this S3 acting on, can be expressed as a linear combination of the original Y basis operator with indices unpermuted. And the linear combination coefficient is exactly the representation matrix d pi of these reducible representations. And in this case, if you view the operator as a tensor of the SUN group, then the space spanned by these Y basis operators intersect with each other. And the flavor specified operators represented by this bounded dot has a certain relation to each other. And I just formally represent this relation or dependency by these yellow lines between dots. And these relations are just what traditional flavor equation depicts. Okay, so what we are trying to do is to resolve this intersection problem. And what we are going to do is to decompose this reducible symmetric group representation into direct sum of irreducible ones. And the new bases are classed into different irreducible space of the S3 symmetric group, and which are exactly the P basis operators we want. And as one can see that the rounded box on the top right, 3 Y-based operators are decomposed into one to one irreducible representation and one totally symmetric representation. And from the group theory, one can know that the corresponding tensors in the same irreducible space of the symmetric group span the same SUNF representation space. And this is shown in the square box on the bottom right, where 2 bluish circles representing the 2 bases representing the space spanned by the 2 bases in this 2-1 symmetric group representation. And these two are overlapped with each other. And the independent components are just directly driven by the corresponding semi-standard Young tableau. And you can see that from left to the right-hand side, one can obtain the independent component of flavors baseline operator, and the independent number of them are reduced from these many dots in the on the left-hand side. Okay. And this is just one example where containing the repeated field and how to relate the original Y-basis operator to the P-basis operator, which are organized in the irreducible representation of the symmetric group. And our problem now is to how to find this conversion matrix between these two operators. Once this conversion matrix is found, then the problem of the repeated field is solved. Okay, and so how to solve this problem? Let's start by an observation. If you permute flavor indices of the repeated fields in an operator, and then you can, by renaming the domain indices of the gauge and the Lorentz parts, then one can find that the effect of the permuting the flavor indices is equivalent to simultaneously permute the indices in the gauge and the Lorentz parts. So this tells us that the representation of the permuting the flavor indices are just those direct product representation or inner product representation of permuting the gauge and Lorentz parts respectively, which can be shown an example here, which I'm not going to detail. So the same conclusion can be obtained through the amplitude point of view, which I'm not going to detail due to the time constraint. From the above analysis, now the problem is converting to find the combine the permutation symmetry of the gauge and Lorentz structure. To do this, you need to take 3 steps. And the first one is to determine what kind of irreducible representation space of the symmetric group that the gauge and Lorentz structure can take respectively. And this is just a counting problem, and they are solved by the sim2int package and explained very well in this literature. However, their work is just limiting to the counting. They cannot find the explicit expression of them. So our work first revised their method to find the permutation symmetry of the Lorentz structure. And what's more important is that we are able to write down the explicit form of them, and simultaneously combine them. These T and M are corresponding the symmetrized gauge and Lorentz factor, and we have a way to combine them into the P-base operator that has the definite permutation symmetry among the flavor indices. So in the following, I will go through the way to how to derive this. So in the following, I will focus on this type of operator, which has only 2 elements in the gauge basis, gauge Y basis, and 4 elements in the Lorentz Y basis. And the first thing is to determine what kind of symmetry that the gauge factor can take. And this is done with the help of the platinum technique denoted by the circle P here. The platinum here is nothing but telling you how to organize the result of the decomposition of the direct product representation of the SUN group into the irreducible representation of the symmetric group. For example, we have 3 anti-fundamental SU3 representation for the 3 DC field here, and the direct product of them yielding 1 10 representation, 2 8 representation, and 1 singlet representation. And the platinum just tell you that the 10 representation is totally symmetric, and 2 8 representation are organized in a 2 1 irreducible representation under the S3 group, and the 1 representation, the singlet representation are totally anti-symmetric in the S3 group sense. So then you know that we can we should have a 2 gauge factor that can be organized in the 2 1 representation of the S3 group. So the problem is how to find this such that their transformation properties has a predefined are related to a predefined conversion or representation matrix of the permutation group. Yeah. So this is where the group algebra projector comes in. And the group algebra, the elements of the group algebra space are just those linear combination of the group elements. And it turns out that one can find all the irreducible representation of the symmetric group from this space. And for example, we can find the basis factor of 2 1 representation here in the blue box. And their transformation under the action of the permutation has a definite form encoded in this representation matrix D. And the idea here to find the symmetrize the gauge and Lorentz group factor is to introduce the group algebra projector induced by the group algebra elements, which where the action of this projector on a function or a tensor with ordered arguments are defined by permutation of those arguments in the function or among the indices of those tensors. And one can verify that the composition rule of these projection operators are preserve the group algebra multiplication rules. And in this sense, one can generate a set of basis function or tensors by acting on the set of group algebra on the given function, such that their transformation properties inherit the transformation property of this group algebra, which is here the D matrix here is exactly the D matrix in the previous slides. So here is just an example of how to obtain the symmetrized gauge group factors by applying proper projectors onto the first elements of the Y basis operators. And
Haolin, you have in total 5 minutes left. Thank you.
Okay, thanks. So so by acting on the other one, it just gives you the same linear dependent basis. Okay, thanks. So you can do the same thing for the Lorentz part, which I'm not going to detail here due to time constraints. And once you obtain the symmetrized group and Lorentz factor, then you can obtain the P basis operator with a definite permutation symmetry just by gluing the proper the gauge and Lorentz group factors with permutation symmetry properly through this CG coefficient of the symmetric group. And the CG coefficient you needed can be read out from this table in advance, which determines what kind of flavor permutation symmetry that the operator can take. Here is just a table of the needed CG coefficient for this type of operator, and this is just a example of the resulting p-basis. How to calculate the resulting p-basis by gluing this CG coefficient and group and Lorentz factors together, and you can finally convert it to the y-basis operators. So and finally, you can obtain the whole KPY matrices, which solve the whole problem, and the independent operators are given by selecting one of the p-basis operators for each resulting representations. Okay, I'll just stop here and waiting for your questions.
Okay, thank you.
Okay, so I see Andreas raised the hand, so please go ahead.
Great, thanks. So how labor intensive is this process, and what's the prospect of making it automatic? Like
we have a package doing the whole places automatically, and will be released very soon. We still have some user interface problem need to tune, but in new feature you can use the program to generate these things automatically. Does that answer your questions?
Yeah, great, thanks.
Okay.
Yeah, and Tom, please.
Yeah, just a follow-up question. So this package, I mean, do I understand that then at some point in this package, there's some numerical evaluation that you have to do?
Oh yeah, yes. Absolutely. For the this is the part I skipped. So once if you wanted to, for example, for the group vector, if naively if you permute the group tensor, and then you get a group tensor, the permute the indices of the group tensor, then you get an group tensor that looks not like the original basis. Then what you do is to numerically convert them as a linear combination of this original one.
Yeah, so I guess my question is, conceptually this is, yeah, so conceptually this is you know, a numerical implementation just from the start is straightforward. You just do it just numerically from the very first, just to say I want to symmetrize it numerically. So the difference between just doing that from the without doing any of this extra stuff that you've done, at what point do you see, like in a program, that you start to run out of computer power from the most naive approach? At what point does your approach become important? Like a master.
Actually, we did that's a very good question. Actually, we if I understand correctly, let me see. Yeah, actually we can obtain the matrix for this reducible representation directly by some numerical one. Without applying. You're right. Actually, we did that, and probably that one was more efficient. Actually, but we still have some bugs related to this approach. But originally, why we did this is that by symmetrizing these factors with group algebra projectors, you don't need to calculate the matrix every time. Every time for each types of operators. These metrics are computed in advance just for one time. If you symmetrize this basis. Initially, we
actually from a sorry.
Yeah.
I guess I was asking. So you were saying that from a computational point of view, it's actually more efficient just to start with the Y basis, apply the permutation to each of those elements, and then numerically check how many of the resulting operators are independent. That is more efficient. Is that what you said?
So I'm not sure I understand. Probably Minglei can answer these questions.
Can I want to add a comment? If I understand Tom's question correctly, actually for the Lorentz part, we are not doing anything numerically. As Haolin showed that in the gauge part, after we permute the gauge tensor, we use something like the inner product to find numerically what's the coordinate under the Y basis after the permutation. But for the Lorentz part, we don't do anything numerically. We reduce the permuted Lorentz structure systematically towards the Y basis. Towards the Y basis using those relations. Yeah.
My question again is like, at what point this becomes important? Just, but okay, I guess that's interesting. Yeah. Makes sense.
Right. So yeah, sorry. I think probably the further discussion can be moved to the Slack, and our co-host will put the Slack link there, if that's fine. Yeah. So yes, then thank you, Haolin, again for the very nice talk, and then the time will be given to the next speaker, Minglei. So